Hi, this lesson is about the definite integral. So the definite integral is what you see here. That's read as the integral from a to b of f of x dx. And that's defined to be the Riemann sum. So the definite integral represents the area between f of x and the x-axis on the interval from a to b. So this should look familiar. So the right side is our Riemann sum. So let's talk about this notation, the integral notation. The integral sign or integral symbol is indicated like this. The function that you're taking the integral of is called the integrand. The dx is called your differential. It is also telling you what you're taking the integral with respect to. So it's with respect to x with this notation. A and B are called your limits, where A is the lower limit of integration, and it's always written at the bottom, and B is the upper limit of integration, and it's written at the top of the integral. All right, integration is the process of finding the integral or calculating the integral. So, in general, your integral from a to b of f of x dx is the signed area of the region between the graph of f of x and the x-axis from a to b. Now, signed means that your area can be positive or negative. That's a little different than what we're used to when we calculated areas in geometry. We always got positive results. But when you're talking about area on an xy plane, the placement of where that area is matters. So for example, a graph like this first one here, example 1, shows that this curve goes from a to b. This is your function f of x, and part of the area between the curve and the x-axis is positive, and there's a small part below the x-axis that's here. So the positive parts are above the x-axis, indicated by the plus signs, and the negative part is below. The total area between f of x and the x-axis from a to b has a net area that is positive. And I know that because there's more positive parts shaded than negative parts. Example 2 has a different result because I again have a function f of x defined from a to b. There are some parts that are positive, like here, this little piece here, and another part here, but most of the area is actually negative between the x-axis and the curve that's below the x-axis. So my net area here would be negative. So some areas under the curve can be found by using geometry. And so geometry would be using formulas that you're familiar with, like areas of squares or rectangles, triangles, circles. So let's look at a few examples of that. Find the exact value under the for the area under y equals negative 2x on the interval from negative 2 to 5. All right, so I've drawn the picture here. Negative 2x is a line, so it's the line from negative 2 to 5, and these are the 2 points that you see right here. It also goes to the origin, so the line extends across from left to right. When I look at it from this perspective, I've created 2 triangles. One I've called triangle 1, which is above the x-axis, and one that I'm calling triangle 2, which is below the x-axis. The triangle above the x-axis will be a positive area, but the triangle 2 is going to be a negative area. So remember, the formula for the area of a triangle is 1/2 base times height, and we can certainly compute what our base and height is in triangle 1 and 2. So let's calculate the area for triangle 1. So it's 1/2 base times height. Well, my base here is 2 units, and my height here is 4 units. So I have 1/2 times 2 times 4, which gives me a result of 4. Now let's compute the area for the second triangle. Now, here I have a base of 5 units, and here I have a base of 10 units, but I know that in general the entire area is going to be negative because it's below the x-axis. So I put a minus sign here. So it's negative 1/2 base times height, 5 times 10, which gives me a result of negative 25. So the net area of the entire curve of negative 2x from negative 2 to 5 is the sum of our two areas, which is 4 plus negative 25, which is 4 minus 25, which gives us a total area of negative 21 units squared. But remember that the integral represents area. So although negative 21 is my calculation, I just want to point out is that this represents the area underneath the curve of negative 2x from negative 2 to 5, and it has a value of negative 21. Okay, so let's do another example. I want to find the area under f of x equal to the absolute value of x plus 2 on the interval from negative 4 to 1. All right, so the absolute value function, these look like v's, and so I want to know what it looks like from negative 4 to 1. When you plug in negative 4, you get the point negative 4, 2. When you plug in 1, you get the point 1, 3. The point where the curve meets in a corner is negative 2, because at negative 2, that's when this function equals 0. So that's where the v, the corner of the v, occurs. So I again have created two triangles. And because I have two triangles, I can use my formula for 1/2 base times height. But this time, my two triangles are above the x-axis. So one will not be negative. They will both be positive areas. So the first triangle is right here, and that has a base of 2 and a height of 2. So that's where you get this calculation, 1/2 base times height. And the second one, well, that has, over here, the second one has a base of 3 and a height of 3. So that's what you see here. So when you compute this, you get 4/2 plus 9/2, which is 13/2. And so that's your calculation for the area. But again, remember that this means that 13/2 is the integral from negative 4 to 1 of the absolute value of x plus 2 dx. All right, let's do one more where we're using geometry. We want to find the area under the curve y equals the square root of 9 minus z squared on the interval from negative 3 to 3. Okay, so this one actually is a semicircle. And so, although it might not be obvious right away, once you start practicing this, it might help you. If I were to square both sides of this equation, you would get y squared equals 9 minus z squared. And if I move z squared over to the right, to the left, you get z squared plus y squared equals 9. You might recognize that as the equation of a circle with a, so this is a circle with a center at 0, 0 and a radius of 3. But since I'm only looking at the positive square root, not the negative square root, I only want the top half of the circle, the semicircle, which is what you see right here. So when x is negative 3, when z is, this is a z value here. When z is negative 3, your y is 0. And when z is 3, your y is also 0. So you get these 2 points. And when z is 0, you get this point. And so that indicates that your radius is 3 all throughout the semicircle. So that means we're going to use the formula for a circle. So the area of a circle is here. This is pi r squared, where your radius is 3. But we only want half of the circle, so you have to take 1/2 of that. So it's 1/2 pi 3 squared, which gives you 9 over 2 pi. And that's your calculation for the area. But keep in mind that that value represents the integral from negative 3 to 3 of the square root of 9 minus z squared dz. Or you can think of it as, because circles are symmetric, that's also the same as the integral from 0 to 3 of 2 square root of 9 minus z squared dz, because that would be just a quarter of a circle like what you see right here. And if I double that, well, I would get the whole semicircle. So either one of those integrals would represent the area. Okay, so let's get back to Riemann sum. The also allow you to find areas under a curve, exact calculations, but first we need to know several power sums. So power sums are special summations that have actual formulas to give you the value of the sum without having to do the individual computation, adding up all of the individual terms. So the first power sum says that if you have a sum as j goes from 1 to n of j, which basically means you're adding 1 plus 2 plus 3 all the way up to n, that you get the value of that sum by plugging it into this formula right here, n squared over 2 plus n over 2. Similarly, the sum as j goes from 1 to n of j squared, well, we know that that means 1 squared plus 2 squared plus 3 squared, etc., all the way up to n squared. And we can get the value of that summation by plugging it into this formula, n cubed over 3 plus n squared over 2 plus n over 6. So these formulas are actually really handy. We're going to use them when we evaluate Riemann sums, but also if your n is a very large number, it's not convenient to do this. It's kind of tedious, takes a long time, versus just plugging in the value of n into the formula. And then finally, we have one for j cubed. So the sum as j goes from 1 to n of j cubed, we know that that's 1 cubed plus 2 cubed plus 3 cubed, etc. And we get the value of that summation by plugging it into this formula, n to the 4th over 4 plus n cubed over 2 plus n squared over 4. All right, so let's compute the area under a curve using the Riemann sum, and these power sums are going to help us to do that. All right, so this curve should look familiar. Y equals negative 2x from negative 2 to 5. So we just did this problem a few minutes ago using the formula for the area of rectangles. And so again, I've duplicated the graph here for you. So we should get the same result. If you recall, when we did it with the formula for the area of triangles, the first triangle was positive, the second triangle was negative, and the net area was negative 21. So if we do this with Riemann sums, we should get the same result. All right, so remember, to use Riemann sums, we need to figure out what our delta x is. So as a reminder, delta x is b minus a over n. Well, our a and b are right here, negative 2 comma 5. So that's 5 minus negative 2 over n, which means my delta x is 7 over n. All right, but I also need to know what my function values are at every ith interval, meaning at every ith rectangle. Remember, Riemann sum is based off of the concept of areas of rectangles. So if I'm starting at negative 2, then the next one over will be negative 2 plus 7 over n, because delta x is 7 over n. And then you would keep moving through this space by adding 7 over n units. So the way you indicate that for every ith rectangle is you start with your starting value here, negative 2, and adding 7 over n times I being the rectangle that you're on. So if I is 1, you're on the first rectangle. If I is 2, you're on the second rectangle. And that will give you the corresponding heights of each ith rectangle. Okay, but we know that our function is negative 2x, so when you plug it into the function, you have negative 2 times the input value, which is negative 2 plus 7i over n. All right, so now let's put this all together in your Riemann sum. So area is equal to the limit as n approaches infinity. Remember, n is the number of rectangles. And so as n approaches infinity, That means that there are infinitely many rectangles that make up the space that's shaded here in this graph, so that there are no spaces that are lost, overcounted, or undercounted like we did when we were estimating in the previous lesson. All right, so from this step to this step right here, I just distributed the -2 across this expression. So we get 4 minus 14i over n. Okay, so now remember, the 7 over n is not changing as I changes. So this does not change as the I changes. So I'm actually going to pull that and put it in front of the summation like I did here. So I have the limit as n approaches infinity of 7 over n times the sum of 4 minus 4i over n. Okay, summations, if you recall, we talked about linearity properties of summations in the previous lesson. Summations can be separated out, like the way I'm doing in this line here. I have the limit as n approaches infinity of 7 over n times the sum as I goes from 1 to n of 4 minus the sum as I goes from 1 to n of 14i over n. Okay, but I'm trying to isolate this I here because then I'll be able to use one of my power sums. So in this line here, all I did was that I put the 14 over n in front of the summation. And again, that's okay because only the I is changing. Okay, so now we're ready to replace the sum of I, this here. This is a power sum that we talked about a couple minutes ago in the next line. And the sum, this one here, if I'm adding 4n times, that's the same as 4n. That's, again, one of the linearity properties for summation. So in here, the power sum gets replaced. The sum of I is equal to n squared over 2 plus n over 2. Just a reminder, that's what we got right here. So I'm just applying that formula. Okay, so let's get back to where we were. So now I am ready to distribute here the -14 over n across those two terms. So that leaves me with the limit as n approaches infinity of 7 over n times 4n minus 7n minus 7. In the next line, I just combine like terms. 4n minus 7n gives me the limit as n approaches infinity of 7 over n times -3n minus 7. Now I'm ready to distribute the 7 over n across here. So I get the limit as n approaches infinity of -21 minus 49 over n. But as n approaches infinity, this term goes to 0. So my answer is -21, as we expected. Okay, let's do another one with the Riemann sum. So we want to use the Riemann sum to find the area under y equals to x squared on the interval from 0 to 1. So we actually did this problem in the previous lesson by estimating the area using left-hand endpoints, right-hand endpoints, and midpoints. And we got estimates of the curve. And at the time, I told you that the area is a third. So now I'm going to be able to prove it to you by using the Riemann sum. All right, so first we find delta x. So delta x is the difference in your interval. So it's 1 minus 0 divided by n. So my delta x is 1 over n. Your function value, which are the heights of your rectangle throughout the space, is f of I over n. So if you start at 0 and every rectangle has a width of 1 over n units, this one is 1 over n, this one is 2 over n, this one is 3 over n, and if you get the idea, there's infinitely many of them. This one here is I over n until we get to 1. So for any rectangle, we're going to say that the input is I over n, where I goes from 1 to n. So since our function is x squared, that means it's I over n squared. All right, so now I'm ready to put that together in your Riemann sum. So the Riemann sum is the limit as n approaches infinity of the sum as I goes from 1 to n of I over n squared times 1 over n. So remember, this is the height of the rectangle, and this one here is the width. So we are adding up infinitely many areas of rectangles on the space from 0 to 1 for x squared. Okay, so like I did in the previous example, I'm going to pull out the 1 over n, put it in front of the summation, but after the limit. Then this 1 over n squared here gets combined with the 1 over n on the outside. So that leaves me with the limit as n approaches infinity of 1 over n cubed times the sum as I goes from 1 to n of I squared. Now I squared is also a power sum. So as a reminder, we go back. Oops, went too far. Our power sum for I squared is right here, n cubed over 3 plus n squared over 2 plus n over 6. So that's exactly what we're going to replace the sum of I squared with. So let's go down below again. So here's where we make our replacement. So I have n cubed over 3 plus n squared over 2 plus n over 6. Okay, in the next line, I'm distributing this 1 over n cubed to that power sum. So that simplifies to the limit as n approaches infinity of 1/3 plus 1 over 2n plus 1 over 6n squared. And as n approaches infinity, these two terms go to 0. So your answer is 1/3. That's the exact area under the curve from 0 to 1 under x squared. Okay, here are some properties of the definite integral. So if your limit values a and b, if a is less than b, and they usually are, that's the same as saying the negative of the integral from b to a. So if these limits change position, then the sign changes, which is what you see here. The second one says that if a equals b, then the integral from a to a of f of x dx is 0. Right, so that makes sense because remember, the integral represents the area under a curve. Well, if I'm going from a to a, that means you're at a single point. There is no area under a single point, so that's why we get 0. Third one says that if you have the integral from a to b of c dx, where c is a constant, well, that's just c times b minus a. And so if we look at this from a geometric perspective, it makes a lot of sense. A constant is basically a horizontal line. So if I have a value here that I'll say is c, that goes from here to there, then the area under the curve of this constant is basically a rectangle with a width of b minus a and a height of c. So the area for a rectangle is length times width, so that is c times b minus a, which is exactly what we said. The fourth one says that if you have the integral from a to b of f of x plus or minus g of x dx, well, you can take the integrals individually and add or subtract them. The fifth one says that if you take the integral of c f of x dx, well, you can definitely put the constant or the coefficient in front and then just integrate f of x and get the same result. And the last one says that if you have the integral from a to c of f of x dx and the integral from c to b of f of x dx, then that must equal the integral from a to b of f of x dx if C is between A and B. So remember, the integral just represents areas. So if you're adding two areas together, then it just gives you one bigger area, which is what we have here. Okay, so let's use these properties. So given that the integral from 0 to 1 of x squared dx is a third, remember we just found this with our Riemann sum, we want to find the value of the integral here from 0 to 1 of 4 minus 3x squared dx. So we'll be able to use some of the properties above in order to do that. Okay, so I have the integral of 4 minus 3x squared dx. I'm going to separate that into two separate integrals, and I can do that because of property number 4. So then I have the integral of 4 dx minus the integral from 0 to 1 of 3x squared dx. All right, so in the next line, I'm actually going to put the 3 in front of the integral here, which is what you see here. So I'm using the fifth property above. So I have the integral of 4 dx minus 3, the integral of x squared dx. Well, 4 is a constant, so I can use property number 3 here. So that's just going to be 4 times the difference in your limits, which is upper limit minus lower. So it's 4 times 1 minus 0. And then this one, we know that this integral is a third, so it's just 3 times a third. So you get 4 minus 1, which gives you a value of 3. So that means that the area from 0 to 1 of 4 minus 3x squared dx has a value of 3. Okay, so let's do another one where we're using the properties. So you're given that the integral from negative 1 to 5 of f of x dx is negative 3, and the integral from negative 1 to 5 of g of x dx is 7. And we want to evaluate the integral from negative 1 to 5 of 4 f of x minus 2 g of x. Well, we will be able to use actually properties 4 and 5 above, because I have a difference of two functions, and I also have coefficients in front of both functions. So the first thing I did here was I took the coefficients in front, and I separated the two integrals, the two functions, into two separate integrals. Then in the next line, I substituted the values of the integrals which are given in the problem. So the integral for f of x has a value of negative 3, so that's 4 times negative 3. The integral for g of x is 7, so that gives me minus 2 times 7. So negative 12 minus 14 gives me a value of negative 26. Okay, so here's another one. We have that the integral from negative 2 to 3 of f of x dx is negative 5, and the integral from 3 to 6 of f of x dx is 18, and we want to find the integral from 3 to negative 2 of 7 f of x dx for part A. So notice that my limit values have switched. So, and that was the first property. So that means that the value of the integral is going to be its opposite. And I also have a coefficient of 7. So this is equal to 7 times the integral from 3 to negative 2 of f of x dx. But we know that from negative 2 to 3 is equal to negative 5. So when you switch the limit values, you take the opposite sign. So this becomes 7 times 5, which gives me a value of 35. For part B, you want to find the integral of negative 2 to 6 of f of x dx. So here, you need to realize that you're basically going to be adding two areas. So the first integral is the area from negative 2 to 3, and the second one starts at 3 and ends at 6. So the area that we want from negative 2 to 6 is just the sum of the two integrals, which is negative 5 plus 18. So the actual value of the integral from negative 2 to 6 is 13. All right, here's another one. We want to evaluate the integral from pi to pi of sine squared of x dx. So remember, one of our properties was that if your upper and lower limits are the same, then there is no area under the curve because it's a single point. Therefore, the value of this integral is 0. Okay, here's one more. So given that the integral from 0 to 10 of f of x dx is 25, and the integral from 0 to 8 of f of x dx is 11, we want to find the value from 8 to 10 of f of x dx and the value from 10 to 8 of f of x dx. All right, so first I drew a picture. So let's say our function is this curve that I've shown here in green from 0 to 10. And so all the shaded area in green represents the first integral. And we know that that has a value of 25. Then the second integral from 0 to 8, I've indicated in this orange color. And so the part that I've shaded in orange is the second integral, which has a value of 11. So I need to find the value of the integral from 8 to 10. Now the integral from 8 to 10 is this part here on the right, which means that I have to take the big area in green and subtract away the area indicated in orange. So I have to compute this in order to get the integral that I'm interested in. But we know those values, they're 25 and 11. So the integral from 8 to 10 has a value of 14. And once we know that, we can easily answer the second part of the problem, which says to find the integral from 10 to 8 of f of x dx. Remember, when you switch the limit values, that just means that your value, that the 14 is just going to take the opposite sign. So the value of the integral from 10 to 8 is negative 14. Okay, so that's it for this lesson. Try doing the homework. Good luck.